Okay, so welcome to Math 349 Operations of Order. And so what I want to do today is I want to continue talking about generating functions. And so last time we were looking at trying to count how many paths could you have on a grid going from bottom left to top right. We first counted how many paths there were when you can only move east and north. And then we were looking at trying to count how many ways can you do it if you must always stay on or below the main diagonal. And we're going to see that there's a nice generalization of the Fibonacci numbers lurking in the background. The generating function is going to be a lot worse. Some of you have mentioned to me that you're in a probability class right now where you are talking about generating functions and generalizations of generating functions, moment generating functions. There's a lot of stuff you can do with these. I thought I would just put in a few of my favorite identities or facts that you can get using generating functions. So the first, does anybody recognize the function x divided by 1 minus x squared? Anybody remember where we've seen this? We did. What were we studying where it came up? Not Benford. So this was the Fibonacci numbers. So the generating function for the Fibonacci numbers is the sum of, fn x to the n, and that turns out to be x over 1 minus x squared. It shouldn't surprise you that the Fibonacci numbers are related to this. I'm evaluating this at 1/10. I'm taking x to be 1/10, and I get the fraction, 100 divided by 9899. And when you look at the expansion of that, 0.01, 01, 02, 03, 05, 08, 13, this looks suspicious. How did I get a fraction whose digits are essentially just the Fibonacci numbers one after the other after the other? Well, what I'm doing is I'm putting in the generating function 1 over 100. Do you think it's always going to keep giving me Fibonacci number after Fibonacci number, or do you think it's going to break down? Break down why?
Because there's only two spaces.
There's only two spaces, so eventually I'm going to have a 3-digit Fibonacci number, which is going to carry over. When the numbers are small, x is 1 over 100. So this is giving you some separation in the digits. So it's nice to just think about this and play with this for a little bit. Well, if I wanted to have it last a little bit longer, if I did 1 over 1,000, I get 1,000 over 998,999, and now it's going to be Fibonacci for a little bit longer. You might be able to guess what the next special number would be for the fraction. We've got 2 data points. What do you think the next one would be? So 10,000 for the numerator, and what about the denominator? Yeah, I think that's how it would be. We had 19829s, 291839s, 391849s. So see if you could prove something like that holds in general. But again, trying to generate problems that you can do. When you're writing a textbook, when you're writing a book, you want to have problems for students to look at. And then of course, there could be other things you might want to try to do. So other fun functions, the x over 1 minus x squared, this was coming from the generating function g of x was the sum of x to the n, which was 1 over 1 minus x. And then we applied the operator x d by dx. When we applied that operator, we then got the sum of n x to the n equaled x over 1 minus x squared. So in particular, if we take, x equals 1 over 100, it's going to just give us a number which is 0.01, 02, 03, 04. There's the integers. This will take a lot longer before things are going to fall back and reinforce. All right. I'm just showing you some of the things you can do with Mathematica. I am not always the best programmer. So for a lot of times, I just care about, can I find out what I need to do? And so d g of x means take the derivative of g of x with respect to x, then multiply by x, and then simplify. And so Mathematica does all of that. Unfortunately, I don't know how to then say, and I want to call that new thing you get after simplifying, call that function h of x. I'm not quite sure how to do that. So what I did is I just had it simplify and printed that out as the output. Then I cut and pasted that output and then defined my h of x like that. I really should learn how to do it better. if somebody wants to teach me, I am always willing to learn. Just what is the way to just do that in one line? And now I can get my fraction, which is going to just be the list of squares. So yeah, these are just some fun relations you can get with generating functions, but they do allow you to evaluate certain sums very nicely. Just going back to the Fibonacci numbers, one of the first questions we have whenever you see an infinite sum should be, does it converge? And we know, so does it converge? Does anybody remember the upper bound we had on the Fibonacci numbers?
Was it 2FN? No, it was
Yes, it was 2FN, and then we could use that to feed back in on itself. And so the nth Fibonacci number is at most. No, you got your Fn plus 1 is at most twice Fn, which is at most 2 squared Fn minus 1. So if you just repeat it, how large is Fn? It's at most 2 to the n. So we know this is at most 2 to the n. So converges if the absolute value of x is less than 1/2 by the geometric series formula. So when I'm looking at this generating function, it's not initially clear that the sum is going to converge. I can write down whatever I want, but it's not clear that the sum is going to converge. At the end of the day, I get it's x over 1 minus x squared. That makes me think it probably converges. I'm getting a nice answer at the end, but maybe I'm doing a bunch of illegal things and getting something at the end of the day. It's not that bad to show that this converges. All we need is some rough growth rate on the Fibonacci's. Now, this tells us that x has to be less than 1/2. X can actually be a little bit larger than 1/2 and have it still converge. Why do you think x can be larger than 1/2 and still have it converge? Not less than 1. Because if we take x equals 1, then you're going to get the sum of the Fibonacci numbers, which is going to explode. So 1 is too far to push. Anybody have any thoughts about how large we could push it? So what can you tell me, how large is the nth Fibonacci number approximately? That's an upper bound. We know the nth Fibonacci number is at most 2 to the n, but 2 to the n is overkill. We then had Binet's formula, and Binet's formula told us that the nth Fibonacci number is about the golden mean. It was actually 1 over root 5 golden mean to the n minus 1 over root 5, blah, blah, blah. But we know it's going to work as long as the absolute value of x is less than 1 over phi. Phi is 1 plus root 5 over 2, as Fn is going to be less than equal to p to the n for n big. And by big, I mean 3, something like that. It sets in very quickly. But with Binet's formula, we know the Fibonacci numbers grow at essentially the rate of 1 plus root 5 over 2 to the n. Now, of course, we've got to be a little bit careful. We use the generating series to find the Binet formula. And so if I'm not using the Binet formula to talk about I've just got to be very careful which order I do things. You always want to watch for this when you're presenting material. Am I doing something circular? No, I know this series converges. I know it converges as long as x is less than 1/2. I can use this to prove Binet's formula. And now that I have that, I can go back and revisit this and I can ask, how big of an x can I take and still have this converge? And so as long as x is less than the golden mean, 1 over the golden mean, this will converge. But you always want to be thinking whenever you see an object, does it exist? Okay, so we talked about the grid problems last time, and we gathered data. And one of the hardest ways to make sure you gather data is to choose a way to go through all the possibilities so that everything that could happen is counted and nothing is counted twice. We saw this earlier when we were trying to count how many gaps do we have of a given length if you look at all Zeckendorf decompositions of numbers between Fn and Fn plus 1. And that's where we had this xi k, or xi I plus k. It would be a gap of length k starting at I. And we just count how many times that happened. So we always have to be extremely careful that we never double count and we never move. And so let's try to consider the problem of counting paths. And let's say we can't cross the main diagonal. 1, 2, 3. 1, 2. I think I do a better job drawing if I draw the diagonal first and then put the other stuff in. So here is 0, 0. Here is NN. And I want to look at paths that don't cross the main diagonal. Okay. So let's let Cn be the number of paths from 0, 0 to n. I'm sorry, I'll use lowercase here, to nn that never go above the diagonal. And we only move east or west. North, thank you. So cultural trivia question, who were the witches mentioned in the original Wizard of Oz? East, west, and there was one other. Nope. South you don't get until you get to the cartoon. Glinda was the good witch of the north. And then the evil witches were the east and the west. How many people out of curiosity have seen Wizard of Oz? Okay. Just always curious to see which movies have survived. So we want to count how many paths there are. Now, if I start looking at what goes on, one possibility is I have to take a step east. All paths have to begin like that. What happens if I take a step north now? I can only go east, but I claim if I go east-north, I'm in a great situation. Why is this a great situation? I'm sorry?
There's only one move that can follow.
It's more than just there's only one move that can follow. How many paths are there from here to NN? I'm sorry? Why 20 paths? Oh, so sorry. I mean, how many paths are there from this point onward that do not cross the main diagonal? Why 10?
This last class it was 20 for the whole grid.
But again, some of those paths go up and down. I want a path that stays just below. And don't look at this as a 4x4 grid. This is supposed to be an n by n grid. Due to budget cuts, I'm not able to draw the infinite or the very large general case. But let's think about what's happening. We're trying to understand Cn. We know we have to start off by moving east, right? So we move east, and then we have two possibilities. We can move east again, or we could move north. Imagine we go east-north, and we're now at this blue point over here. I'm sorry? So don't focus on the fact that this is a specific grid. It's supposed to be an arbitrary n by n grid. Okay. Originally, Cn was the number of paths that don't cross the diagonal starting at 0, 0. I've now done one north step and one east step. How many north steps are left? n-1. How many east steps are left? So how many paths will there be from here that don't cross the main diagonal? C of n-1. I've used one north, one east, so I have n-1 east, n-1 north left. So once I take a east step followed by a north step, I know exactly how many paths are left. It's Cn-1. I'm getting a recursion for Cn in terms of the previous stuff. And so we'll assume that we've already calculated Cn-1. Unfortunately, we could go east, and instead of going north, we could go east-east. Do we know how many paths there are if we're here? So if we go east, east, this is not going to be a C with a smaller number, right?
This is n minus one minus one.
No, because we don't have a square grid.
N minus one, choose n minus two.
We don't have a configuration we know. What would be great for our next moves from here that would bring us to something we know? So north, north. So if we go over here and then we do two norths, then we would be in good shape. So over here, if we then do over here, we have another east and a north. And then here we would have an east and a north. And here we would have an east and a north. And so if we do east, east, north, north, what would the answer be? Cn minus 2. But notice this is beginning to become horrible in terms of how many paths there are, right? This is the east, east, north, north. I've got to now do east, 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 north. I could try to do this, but there's so many possibilities. I need something that's going to simplify a little bit nicer than this, a little bit cleaner than this. Some of these paths become very nice. They go into a previous thing. What made this path of east-north nice? What made east-east, north-north nice? Same number of easts and norths. So maybe what I should do is I should look at all the paths, and I should look at paths that have the same number of easts and norths in the first so many terms. So one of the hardest things in mathematics goes all the way back to geometry. Do you remember auxiliary lines? You're doing a geometry problem, and if you draw this line or these lines with these circles in just the right way, all of a sudden you have everything you need to do to solve the problem, but you have to figure out where to draw the line. If you're doing a problem involving Pythagoras, right angles, you probably try to draw lines that give you more right triangles. And there's some idea. The hard part here is to try to figure out what is a good auxiliary quantity to help us understand the recurrence relation. We're trying to find a way to relate Cn to smaller values, to smaller paths. And then we can just build up, from our relation. So what we've noticed from these two things over here is, so observation. It's nice when have the same number of east and north steps. So what happens when you have the same number of east and north steps? Where will you be? Along the diagonal. So that moves us to the diagonal. So maybe that's a good way to study things. So what we're going to do is we're going to introduce Bn. This is the number of paths from 0, 0 to nn that first hit the diagonal at nn and always below. Before then. Okay, so let's try to draw what this means. Here's my diagonal. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Not well drawn, but hopefully close enough. Okay, so we start off down here at 0, 0. We want to get up here to say, NN. And now let's consider a path that stays below the main diagonal or on the main diagonal and never crosses. Do you agree that no matter what path I take, as long as it doesn't cross the main diagonal, has to have a place where it first hits the main diagonal? Where could that place be? Could be, well, so we don't want to count 0, 0, because then trivially everything will. There's at least one point where it's got to be on the main diagonal after 0, 0. And so everything has to hit the main diagonal at some point. Maybe it hits it earlier. So let's look at all the paths that first hit over here. So each path has a first hit of the main diagonal, of the diagonal. So what does that mean? If this is the first hit, it means I was never on the diagonal before that. What must my first step be? My first step has to be an east step, right? What about my second step? Has to be east. What about my last step? Has to be north. What about my second to last step? Has to be north. Why can't it be east? I would have been on the main diagonal. So it's got to be something like this. And so now I look at I have a legal pathing through here. Right? And so I can now look and see how many paths can I have in a situation like this. So now we've got to be careful here. So if I do it like this, there's 2 paths. But if I look at those paths, one of those paths crosses that diagonal. So it might actually be better. Okay. No, I'm saying if we wanted to look at paths like this, I could now take a path that goes north and east, and that would be above the diagonal. And I would also have the path that goes east and north, which would be below the diagonal. We're choosing things to always count paths that stay on or below the diagonal. So over here, I would have 2 paths to count because one path could be above and one path could be below.
You have diagonals within. I don't understand why you do that arbitrary diagonal on that one square.
Because I'm basically trying to say it's like we have the game on a smaller board now. But the problem is when I try to analyze it on the smaller piece, I could have some paths that go above the diagonal and some paths that go below the diagonal. And so rather than using all the information, sometimes it's better not to use all the information you have. We know the first step has to be east. What about the last step? Has to be north. So now let's just use just that information. And so now let's say I want to try to go from the bottom over here, which is going to be 1, 0, to this dot over here, which is going to be, if this green dot is at n, this would be at n, n minus 1. And I want to now look at all the paths from here to here. Well, if I draw my diagonal, could I ever cross that blue diagonal? No. What would happen if I crossed that blue diagonal? I'd hit the main. So really, if I use just going from 1, 0 to n minus 1, I'm just counting how many legal paths are there that stay below the main diagonal. This is a slightly smaller problem. So this is now, how many paths will there be? I'm sorry? Without hitting the blue line. Not just 1, I'm sorry. Not bn minus 1. You're close. You're off by 1 letter. Cn minus 1. I'm allowed to hit the main diagonal in the blue. I just have to stay below the diagonal of the original problem. So I just care about how many legal paths are there that stay on or below this blue diagonal. So if I want to calculate what is the number of paths that will first hit at little n, I know I start off with an east step. I know I end with a north step. And then how many ways can I fill in the remaining? It's just going to be Cn minus 1. So we get the beautiful fact that Bn is going to be Cn minus 1. Does everybody understand and agree with this? What I love about this is there was more information that I knew, right? I know the next step has to be east, and I know the last two steps have to be north. If I put in all that information, I actually make the problem harder. If any of you expect that for the rest of your life, you are only going to be given the information you need and nothing extraneous and nothing is missing, we have not done our jobs as your professors. Hopefully, you will at least have all the information you need to solve a problem. But you will almost surely have more information than you need, and you have to figure out, what do you really want to use? I think it's very natural to try to push in all the information we know to simplify it as much as possible. I know I've got to start off with 2 easts. I know I have to end with 2 norths. Well, if I do that, it then reduces to a slightly different problem than I'm looking at. I'm defining things that count paths that are on or below the diagonal. And if I did it the original way that we were talking about, I could now go above the diagonal and that wouldn't be a problem. So I think it's actually much easier to write it like this. So now we know that the number of paths that start at 0, 0 and go to NN, and that's the first time they hit the main diagonal, is going to just be Cn minus 1. Yes?
I get this part, how you can touch the blue diagonal.
Yes.
Fine. But in the previous case, when we went 2 east and we had to go 2 north to finish it,
Right.
can you go above the blue diagonal?
In that case, yes. And so we couldn't reduce that to one of the quantities we already studied. We've already introduced Cn to count how many paths there are that are on or below the main diagonal. We've introduced Bn to count how many paths there are that are on or below the main diagonal and first hit the main diagonal at n. If we wanted to do what we had a moment ago with 2 norths and 2 easts, then we would actually be counting just total paths. And that's a different quantity. And so this is just allowing us to reduce things to things we've already seen. Now, that might not be a bad way to do things because we do know a formula for how many paths there are. So if we are able to do that and have something that will stay below, that could be valuable. But we've got to be careful because we're not allowed to hit up. So that would be a great thing to try, is try to see, could you make this problem work and get a nice answer if you start off with 2 easts and end with 2 norths? You would then have something different in here. Maybe then you use our formula for the total number of paths. I haven't seen that done in the books. I'd love to see if that works. I think that would be a great thing to try. And then that might be easier than what I'm about to show you. So the number of paths. Let's count Cn. So Cn, I claim, is going to be a sum. K goes from 1 to n. And this should be Cn. So I'm trying to count how many paths are there from 0, 0 to capital N, capital N. And I'm going to condition based on the first time you return to the main diagonal. The first time, well, I have to at least do something to be a first time. So K has to be at least 1. It could be 1, it could be 2. And I might not return until I get to the very end. Maybe I start off with n steps east and n steps north. So does everyone agree that I'm conditioning based on when I first hit? How many ways are there to have the first hit at KK? No. So I want to know, how many paths are there from 0, 0 to KK such that the first time I hit the diagonal is at KK? I'm sorry, not 1. BK. This is the number of paths from 0, 0 to KK, and we first hit at KK. Now that we're at KK, we have to go from there to NN. So how many paths are there now from KK to big N, big N? Well, this is something very similar to what we saw when we looked at the Zeckendorf decomposition and we looked at the gaps. And we said, I have a gap of length G starting at I, and then I look at all the ways I can choose things legally before I, and all the ways I can choose things legally after I plus G. And I just shifted my indices down. So what should I shift KK down to make this nicer? 0. So I shift it by K, and I go from 0, 0 to n minus K, n minus K. So how many paths are there from 0, 0 to n minus K that stay on or below the diagonal? Cn minus K. And here's my recursion. And so the number of paths from 0, 0 to nn that stay on or below the main diagonal is the sum k goes from 1 to n of bk times cn minus k. You always want to make sure that we don't double count things. Is it possible that we've counted a path twice? Fortunately, the answer is no. Because if I have two paths, they can't be the same if they first land on the main diagonal in different spots, right? So the only way two paths could conceivably be the same is if they first hit the main diagonal at the same spot. Well, that's what I'm doing over here. I'm splitting things off based on where do you first hit. And then once I hit, I've just reduced to a problem I already know. You know, I'm now just counting how many legal paths are there. Now we have two equations. We have an equation involving B and an equation involving C. If you look at it, Bn is just Cn minus 1. So this is just the same as the sum k goes from 1 to n of c k minus 1 cn minus k. So let me just write this on the next page. So we get cn is the sum k goes from 1 to n, capital N, and then it was going to be c k minus 1 c n minus k, I think. So we want to solve this recurrence. How do you think this compares to the Fibonacci recurrence? Why? And so I'll remind you, Fibonacci was fn plus 1 is fn plus fn minus 1. So whenever you're not sure, what should we do to try to get a sense of what's going on? Take some cases. So let's take n equals 0. Well, okay, so if we take n equals 0, we get C0. So I have the sum k goes from 1 to n. Am I? Yeah, so the question is, what do I do for C0? You know, if I look at this formula, I'm a little concerned about the sum. So if we just have C0, it's how many paths do we have from 0, 0 to 0, 0 that stay? I'm happy to, let's tentatively set C0 equal to 1. That seems reasonable, and we'll see if it's consistent with everything else. Let's look at C1. So if I now want to look at C1, k goes from 1 to n. Oh, good. K goes from 1 to 1, so k is just 1. So I would get C0 times C1 minus 0 is just C1. And this is looking. Oh, wait, no, k is equal to 1. So it'd be C0 times C0, right? Which tentatively 1. But what can you tell me about the number C0? What kind of number is C0? We have some dispute in this class. I saw at least one person concerned about C not being declared to be positive. But what kind of number is it? Well, I mean, it's a fixed number, so it's a constant, yes, but what kind of number? Could it be an irrational number? Could it be a complex number? It's an integer. What kind of integer? It's the number of paths from 0, 0 to nn. It's a non-negative integer. We know C0 is a non-negative integer. C0 squared equals 1. therefore C0 has to be 1. So if you think about it, if we look at the special case of a grid with just one thing, there is only one path. So we know by direct computation that C1 does equal 1. Small values we can check. Building on this success, we can calculate C2. So C2 is going to be the sum k goes from 1 to n. So k goes from 1 to 2. So when k equals 1, we're going to get C0, and then we're going to get C2, right? And then when k equals 2, we get C1, C1. Damn it. Did I make a mistake? No, I made a mistake again, sorry. When k equals 1, we're going to get C0, C1. And when k equals 2, we're going to get C1, C0. So what will that be? 2. So our first numbers are 1, 1, 2. So the C's are actually the same as the Fibonacci numbers.
You wanted C0 the same. But
C0 and C1 are both 1, and C2 is 2.
wouldn't it be C0 for the first term?
For C1?
No, C2 equals C0 times C0.
Okay, let's see. When k, we've got this as k equals 1 and n equals 2,
Oh, okay.
right? So when k equals 1, the ck minus 1 is just 0. And then the C2 minus 1 is just 1. So the first 3 terms are 1, 1, 2. It's the Fibonacci's. Yay or nay? Who's buying? So far.
But isn't there only one 2 by 2 grid?
Well, let's think. So let's do a calculation. And so I've got to avoid the main diagonal. So here's one possible path coming up like that. And here's another possible path. And I don't cross. There are 2 paths, and exactly 2 paths. So the sequence starts 1, 1, 2. Who thinks it's the Fibonacci's? And that this is just a more complicated way of writing the Fibonacci recurrence. Well, I'm sorry? Reason to believe it is. How confident are you with 3 data points? Okay, so if I gave you 40 data points and the first 40 all agreed with the Fibonacci's, would you be convinced? Yeah, I can actually give you something in mathematics that works for like 41 to 47 times before it starts to fail. It gets harder to find these things, but what should we do? Well, there's something very simple we can do right now. Calculate C3. So we calculate C3. So this is now going to be, n equals 3. K is going to be in the set 1, 2, 3. So the first thing is when k equals 1, we're going to get C0. And then 3 minus 1 is going to be C2. The next one is going to be C1, C1. And then the last one, when k equals 3, we'll get 3 minus 1 is C2. And then the last one is going to be 3 minus 3, which is 0. Okay. We know C0 is 1. We know C1 is 1. We know C2 is 2, right? So this is going to be 1 times 2 plus 1 times 1 plus 2 times 1. Yes? This equals 5. Do you still think it's the Fibonacci's? Maybe it's a subset of the Fibonacci's. What do you think? I've got 1, 1, 2, 5. Potentially. But it's definitely not the Fibonacci's. It's easy to be misled by small data. If you look at what's going on, there's some interesting relations. I have C2, and if you look over here, every time I move to the right, the index of the first piece goes up by 1, and the index of the second one goes down by 1. And if you look at the formula, that makes sense because I've got C, K minus 1, C, N minus K. So I'm going to be increasing the first one by 1, and the next one is going to be decreasing by 1. I have a C2 here, the sum of the indices is 1 less than that. I have a C3 here, the sum of the indices is 1 less than that. And so there's a couple of ways that we can be playing these games. So can we find out a nice formula for something like this? This should be enough to convince you that this is not the same as the Fibonacci's. The formula becomes a lot worse. For the Fibonacci's, it was a fixed length formula. I only have 2 terms. I always have just 2 terms. Over here, the number of terms in the recurrence grows. This is a much harder recurrence to study. But there is some kind of structure going on. The C3 is related to products of the C's. And if I gave you C4, don't misuse it, I'd have C0, C3 plus C1, C2, thank you, somebody got it, and so on and so on and so on, right? Let's play fast and loose with math for a little bit. We want a generating function, right? There's a natural candidate for the generating function. G of x is going to be the sum, and goes from 0 to infinity, of Cn x to the n. Okay, so let's say I gave you 2 generating functions. Let's give ax is the sum and goes from 0 to infinity of an x to the n, and b of x will be the sum, m goes from 0 to infinity of bm x to the m. And I'm going to let c of x be a of x, b of x. Well, let's think, what happens when I multiply these 2 together? I'm going to have a0 plus a1x plus a2x squared plus a3x cubed plus dot, dot, dot. And I'm going to have b0 plus b1x plus b2x squared plus b3x cubed plus dot, dot, dot. And now I want to multiply. How can I get a constant term when I multiply? What's the only way when I multiply things together that I can get a constant term? A naught, B naught. So A naught, B naught is going to give me my constant term. How can I get a linear term? So which pieces will give me a linear term? So A1x and B naught can combine, right? And then also B1x and A naught. So this will give me A0 B1 plus A1 B0 times x. What if I want to get an x squared term? I could have the A2x hitting the B0. I could have the A1x hitting the B1x. And I could have the A0x hitting the B2 of x. And it's becoming a real mess. But I would have, A0 B2 plus A1 B1 plus A2 B0 x squared. And so on and so on and so on. So when I multiply 2 functions like this, there's a nice way to combine them. And to figure out, here's the new constant term, here's the new linear term. We are going to care about this in the very special case when big A equals big B equals C. So, this is, a general power series. I'll call this, C tilde, so it's a little bit different from the C we're looking at. But for us, we'll take A of x equals B of x equals, C of x, which is the sum, and goes from 0 to infinity of Cn x to the n. Now, this expression looks very similar to what we had before. So now what we get is we will have C of x squared is all the A's and B's are C. So it's just going to be C0 times C0 plus C0, C1 plus C1, C0, X plus C2, I'm sorry, C0, C2 plus C1, C1 plus C2, C0, X squared plus dot, dot, dot. Does everyone agree that that's what we get when we square C of X? This should look really familiar. If we go back, C0, C0 is just C1. C0, C1, C1, C0 is just C2. So when we look at this, this is supposed to be C1. This was supposed to be C2. What was this supposed to be? C3. So what's the relationship between CX squared and CX? This looks a lot like C of X, doesn't it? We have C1 plus C2X plus C3X squared plus dot, dot, dot. What would you love to have? Do you want to have a C3X squared term? What would you like to have? Yeah, can you just make it a cube? So if we multiply everything by X, this is the same as CX squared is 1 over X, C1X plus C2X squared plus C3X cubed plus dot, dot, dot. Is that related to anything you know? What is that? I'm sorry? This is almost something we know. No? We're trying to understand C of X, right? Doesn't that look, how is this different from C of X? I'm sorry? Well, the X term is correct. It has a C1X, it has a C2X squared, it has a C3X cubed. What's it missing? The C0. So this is the same as C of X squared. I'll move the X to this side. Is equal to C0 plus C1X plus C2X squared plus C3X cubed plus dot, dot, dot minus C0. So that's X C of X squared is equal to C of X. And what does C of 0 equal? 1. So for homework, figure out what C of X is from this. Okay, we have to be able to justify all the steps we've done, but we've just come up with a formula for C of X. So see if you can find C of X, and then using that, see if you can then deduce what the individual C's are. We'll go through and we'll show that on Friday. But again, the goal for this is to do some math that some of you are going to need for what you're writing up, and to use this as a springboard to talk about math concepts and proofs. Okay.